Hello and welcome to another video. Today we're going to be working on implement stack using queues. And this problem is, I would say, not quite an easy problem. It depends on your implementation as well. So I'd say it's closer to a medium problem, but in this problem you're asked to implement a last in first out stack, so a normal stack, using two queues. The implementation should support all the functions of a normal stack: push, top, pop, and empty. And then you want to implement it, you want to have a push, pop, top, and empty. And you can only use standard operations of a queue, which means push to back, peek from front, size, and is empty. And so depending on your language, the queue may not be supported natively. You may simulate a queue using a list or deck, as long as you're using a standard like queue operation. So we cannot use pop from the back. We can't look at like the last element. We can only look at the first element, and we can only pop from the left. And here's this example. So essentially, let's take a look at what it would look like. So you start a stack and you push 1. So like what a stack would look like is you push 1, then you push 2, and then you do top, which gives you the last element, so we return 2. Then you would pop, which would pop this 2, return it, and get rid of it. And then you checking for empty, and it should return false because there's something in your queue. So what we're going to do is we're going to show the way to do this with two queues, and then the way to do this with one queue. And the easiest thing, honestly, I found for this problem, or these types of problems where you're doing stack with queues or queues with stacks, is try a few numbers and like make sure it makes sense. And so what we're going to try is we're just going to try putting in the numbers 1, 2, and 3, and kind of just trying to figure out like, okay, like is their queue okay, basically. And so there's a few ways to do this. So I'm going to show you the two queue ways. So let's just call this Q1. It's going to be a deck. Call this Q2. It's going to be a deck. And in this first example, it's going to be pretty straightforward. So we're going to go through these one by one. So essentially, Q1 will be our main like queue. And you can do this a few ways. Essentially, it's either your push or your pop is going to be O of n, and then the other one will be O of 1. In my case, I decided to make the push O of 1 and then the pop O of n, but either one's fine. Like you can ask, like which operation should I prefer maybe in an interview, and then if they said like they're all equal, then you could do it whatever. But if they said like, oh, we're going to be doing more, well, I guess you can't really do more pops, but let's say you like maybe if you have equal amounts of tops, pops, and pushes, top and pop here would be O of n, so maybe you could swap it around to make push O of n and then top and pop O of 1. So those are some things to think about. But essentially, so what we're going to do is going to be pretty easy. We're just going to insert 1, 2, and 3, and we're going to show what that looks like. So when we push in 1, we're just going to push always into this first queue. And that's pretty much it for the push. We're just going to do like a normal append. And then, so we're going to push in 1, 2, 3, and we're going to show what it looks like to get rid of an element. So we're going to push in 1, we're going to push in 2, we're going to push in 3. And so this is so our first queue is really like a stack, but we're not going to be using any stack operation. So now if we call pop, what we are going to do is so we want to pop this last element, but we can't like pop from the right. So what we're actually going to do is we're going to pop from the left and insert into this first queue. So we're going to pop from here and push to this, which is allowed, right? Pop, we're using a pop left and an append. So what that's going to look like is we pop 1, we push it in, gets rid of the 1, then we pop 2, because that's our first element. Now we push it in, and now our queue is length 1, and now we could say like, okay, when the queue is length 1, then pop that last element, save it in a variable, right? So we're going to pop this, save it in some result variable, and then that's what we're going to be returning. And for our second queue, now we do the same thing again. So we can just say like, while we have our second queue, let's pop and add back to the first queue. So we pop the 1, we add it over here, then we pop the 2, and we add it over here. And so now our queue is, or our 1 is, this, and our 3 is popped. And top is basically the same thing, except instead of returning this 3, you're literally doing the exact same process, except instead of returning here, you save the variable, and then you push it in at the very end over here. So literally pop and push are, pop and top are like a one-line difference with two queues. And so we can write this down. Here's our steps. So push would just be append O of 1, like a normal append, pop, we pop left from Q1 until one element left, or so pop left from 1 and append to 2 until one element left in 1, then pop that element and save it, then pop left from 2 and append to 1 until nothing left in 2. And then top, same as pop, but at the end, append the saved element to 1. So that's pretty much it. Pretty straightforward, right? So that's the approach for this. And then for our big O complexity, so our push would be O of 1 because we're just doing a normal append. But for the pop, we have to take all of our elements from here, put them in here, and then put them back. And so that is going to be O of n. And top, same thing as O of n. So that's one way to do it. And empty obviously is like really straightforward. We are allowed to use the size, so we can just check for the length of it, right? And if the length is 0, then, or if they say we can even use it as empty. So if we can use it as empty, I don't know if like a deck has as empty, but you can just check for the length. And then if the length is 0, then it's empty. Pretty straightforward. Okay, so now we're going to focus on the other approach, which is going to be the 1Q approach. So we're going to go back, delete some of this, and we are going to do the 1Q approach. And the 1Q approach you're going to see is pretty straightforward, but there's going to be a difference. So I decided for the 1Q approach, maybe you could do it both ways as well, but just for me, I decided I want my 1Q to be a reverse stack. And what that means is, let's say if in a stack you would push 1, 2, 3, and it would look like this, I want my Q to look like this. That way, when I pop, the pops and tops are really easy, right? We're just going to pop left, and that would be the same as this. So essentially, I want my elements to be inserted backwards. Now, the way to do this is also pretty straightforward. And so now our pushes are going to be O of n, and our pops and tops are going to be O of 1. And let's just go through the same thing with like a few elements. Let's maybe do 4 elements. So essentially, for the first element, so we're going to have only 1 Q now. So for the first element, it's pretty straightforward. There's nothing there. For the second element, what I'm going to do is I am going to do a normal append, but then I will have a loop that says for the length of the Q minus 1, right? We are allowed to get the length here of the Q. Yeah, so they let you use size, which is like the length. So for the length of the Q minus 1, in this case it would be 1, we are going to pop left and append, which means we're going to take our element, delete it, and put it back here. And so once we do that, our Q will look like this. And now if we want to insert a 3, let's see what that would look like. So we would have 2, 1, 3. And then we're going to say, okay, for the length of the Q minus 1, let's pop from the left and append to the right, right? Both valid operations. So let's look what that's going to look like. We have to do that twice. So we're going to pop the 2, add it to the back. So then we will have 1, 3, 2. And then we need to do that one more time. So we're going to pop the 1, add it to the back. And we'll have 3, 2, 1. So you can see like you can keep doing this. Like we're going to do one more maybe. So if you want to add a 4, you do the same thing. You would say, okay, well, actually, I guess like a slight optimization. I mean, I guess it doesn't really matter. Let me think about that. No, actually, no. You do need to insert the element first. Yeah, you do need to insert the new element first because we're not allowed to insert at the front. So you do have to insert the new element first and then rotate everything around. But yeah, so you would, for a 4, you would add a 4, you would do a normal append, and then you would do this like loop thing 3 times. So after one iteration, you'd have 2, 1, 4, 3 would get pushed out and pop back in, and you would do it 2 more times. So then you would have this, and 1 more time. So 4, 3, 2, 1. So essentially your Q is a reverse stack, and then a pop is really easy because we just pop left, and a top is really easy because we are allowed to look at the 0th element. And that's going to be that. And then for the empty, it's the same thing. Like you just check for the size. So that's the 1Q implementation. I don't think you can make it more efficient. I think you do have to make one of them O of n and then the other one O of 1. But in this case, I kind of swapped it around to show you what that would look like with a 1Q. And we are going to code up the 1Q now. So for init, we're going to have 1Q. So we're going to call it stack, but we're going to represent it with a deck. For push, remember we need to push the element. We're going to do a normal append. So with self.stack.push, or sorry, no, we can't do push. We append x, and now we need to do that loop the length of the queue minus 1 times, because for every element that was in there before that x, we need to rotate it around. So we could do this. We could say for this value that we're not going to be using, length self.stack minus 1. So essentially, like if this was length 3, we would do this twice and so on. And if you want to use an index, if you want to have a for range loop, but you don't want to like actually use this I value, you can just do this underscore, and that'll essentially say like, I don't want to use this value in my actual for loop, but I do need to loop, you know, whatever amount of times this is. So that's how you do that. So we're going to say self.stack.append, and then we're going to have that popped value. You could also do this in 2 lines if you want to save the variable. Self.stack.popleft, which is a allowed operation. So essentially, we're going to pop left, and then we're going to append what we popped left. So if we had something like, say we had 1, 2, we put on a 3, we would pop the 1, and then we would append it over here. And we're going to do that twice. Okay. Yeah. Now for the pop and the top, it's really straightforward because we can just say return self.stack.popleft, because now remember, our stack is set up in a way where it's very easy to pop, because the item that would be popped from a stack is now on the left. Like our queue is a reverse stack essentially. And then here we could say return self.stack 0, also really easy because we are allowed to look at the 0th element. There might be like a top method in deck. I didn't really look into deck too often. I just used the basic stuff in deck, like pop left, push, append, and so on. But we are allowed to use a queue standards operations, including peek pop from front. So if there's a peek pop from front, that's basically that. Okay, and then for empty, also straightforward. So we need to return true if it's empty. So we can say return true if not self.stack, meaning the size of it is 0, else false. So what this will do is it'll just say like, if the stack is length 0, that this will evaluate the true, and then we will return true. Otherwise, it will be false. Oh yeah, but that's pretty much it. So pretty straightforward once you like recognize what you're doing. And I would say for these problems, I think it's pretty important to just like write out your steps and make sure it's kind of correct, because it's very easy to, it's hard to visualize it. So I would try if you do 2 queues, 2 stacks, whatever it is, try to draw them out and see like, okay, here's like a sample operation. Here would be a queue with like 3 elements. Let's try to like put in the 4th element and so on. So let's try to run this. Work. Yeah, and you can see it's pretty efficient. And yeah, I don't believe I used anything that was not allowed. So append was allowed. Let me just double check real quick though. Yeah, so push to back, which is append. Peek from front, which is pop left, and then peek from, or I guess this is the peek, this is the pop. So we didn't use anything that wasn't allowed. And now let's go through the time and space, and we can do this for every single method. So obviously init doesn't really matter. So for push, it's going to be O of n, because we have to essentially reverse our stuff. Then for pop and top and empty, it's going to be O of 1, because we are just doing 1 pop. This as well. And pop left in a deck is O of 1. And you can actually, if you want to, and I did do this in JavaScript, for example, so the way you can make a queue or an array using an object, and then if your like front is deleted, like normally in an array you'd have to shift everything over, but if you use an object with keys, all you have to do is just shift your starting key and your last key, and then your index can just be in your keys. Maybe I'll do the problem on that like later on, but essentially like if your starting key was 1 and your last key was 6 and you were accessing like element 0, then element 0 would be your first key, and if you were accessing like element at index 2 or something, you would just take whatever your first key is and add 2, so it would actually be at like key 3 and so on. So you don't actually have to shift if you do this doing an object. And I did actually make like a deck-like structure in JavaScript that was, I actually tested it against like a JavaScript deck that you could import, and it was about the same speed, so I was kind of happy with that one. Because in JavaScript, it doesn't have a queue either. It has an array, and if you want to use a queue, you have to do like shifts, which are O of n. But anyway, that's too long about that. Okay, so yeah, so this time is O of n, this is O of 1, and for this, So we do have like our actual deck, right? So that's O of n because we are like storing all our numbers. But we aren't using any other data structures. So it is O of n with two queues. So pretty much with two queues or one, it will be the same thing. Like either way, one of your things will be O of n, two of them will be O of 1, or reverse, right? Pop and top are the same. Pop and top are the same time complexity because they're basically the same thing. And your space would also be O of n because you'd have two queues, which is still O of n. It would be total n elements. So you're not really saving anything. It's more just kind of like a cool solution to look at. But yeah, so that's going to be it for this problem. Hopefully you liked it. And if you did, please like the video and subscribe to the channel. And I'll see you in the next one. Thanks for watching.